Let's start by looking at the components used in this project. Number 1, photoresistor. This is the star of the project. A photoresistor, also known as a light-depending resistor, is a component whose resistance decreases as light intensity increases. This makes it perfect for measuring the ambient light level. Number 2, LEDs. 5 LEDs will be used to represent light levels. As the environment darkens, more LEDs will light up, visually indicating the drop in brightness. Resistors. Resistors are used to limit the current through the LEDs and the photoresistor. This ensures the circuit operates safely and efficiently. Number 4, Arduino Mega. The Arduino Mega serves as the brain for this project. It reads the input from the photoresistor and determines how many LEDs should be turned on. Breadboard and connecting wires. These components make it easy to set up the circuit without soldering. This breadboard allows us to arrange and connect all the components in a neat and organized manner. Now let's look at how the circuit is set up. The breadboard is the foundation of the project. The photoresistor is connected to one of the analog pins on the Arduino, allowing the microcontroller to read and change its light levels. The 5 LEDs are connected to 2 digital pins, 2 through 6 on the Arduino. Each LED has a current limiting resistor in series to prevent damage. The Arduino reads the light level from the photoresistor and, based on the brightness, turns on an appropriate number of LEDs. For example, in complete darkness, all 5 LEDs will light up, while in bright conditions, none of them will. This setup visually translates light intensity into the number of illuminated LEDs. Now let's dive into code that makes this project work. The program is written in Arduino's C-based language and consists of a setup and function loop. Defining pins. At the top of the code, we define constants for the digital pins connected to the LEDs and an analog pin for the photoresistor. This ensures consistency and clarity throughout the code. Setup function. In the setup function, the LED pins are configured as outputs using pin mode. The initial light level is read and stored as calibration value using analog read on the photoresistor. Loop function. In the loop function, the Arduino continuously reads the current light level. If the light level drops below the calibration value by a certain threshold, the LEDs start turning on incrementally. Each threshold corresponds to one additional LED being activated. For example, when the LED is 10 units below the calibration value, one LED turns on. At 20 units below, 2 LEDs are on, and so forth. When the light level returns to the bright conditions, all the LEDs are turned off. Lastly, let's take a closer look at the schematic. Power and ground. The Arduino's 5-volt and ground pins supply power to the breadboard. The photoresistor and LEDs are powered through this system. Photoresistor configuration. The photoresistor is connected to a voltage divider circuit. This allows the Arduino to measure the changing resistance as a voltage value on the analog pin. LEDs and resistors. Each LED is connected to the digital pin on the Arduino via a 220 ohm resistor. The resistors limit the current to the LEDs, preventing them from being damaged by the excess current. The schematic ties together all the components to create a functional circuit that can dynamically respond to changes in light. In summary, this project demonstrates how a photoresistor can be used to measure light and control a set of LEDs dynamically. By combining a simple circuit with the power of Arduino, we've created a responsive system that visually represents light levels. Whether you're a beginner or experienced engineer, projects like these are a fantastic way to learn and experiment with electronics.